Okay, so we're working on the fundamental theorem of algebra.
Okay.
And the first question is to solve and find the zeros of gx equals x cubed minus 3x squared plus 4x minus 12.
Okay. This is a cubic equation. In general, cubic equations are extremely difficult to find the zeros, unless they happen to have a certain property, and this one has it. What that property is the ratio of your first two coefficients is the same as the ratio of your second two. In other words, there's a 1 in front of that, so I got 1 over minus 3. Is that the same as 4 over minus 12? Yes, it is. If you find that, then we can factor this by grouping.
Okay.
It's a very, very specific method that you can use to factor cubics. But like I said, those conditions have to be exactly that way. In other words, if I change that 12 to a 13, not going to work. If I change that 4 to a 3, not going to work. They have to be the exact ratio. Okay? Then
Okay.
what I'm going to do is I'm going to group the first two terms together and the last two terms together. And now I'm going to factor the greatest common factor out of each set of parentheses. What's the greatest common factor here on the left?
On the left, 1, right? Does that count?
Include the variables.
Oh,
X squared, right?
yeah.
In other words, I can take an x squared out. What's left behind?
X minus 3.
Okay. And always be checking. Make sure that that multiplies back together to give me what I started with.
Mm-hmm.
I'll take the greatest common factor out of this.
4.
Leaving?
X minus 4. Or X minus 3, sorry.
Right. That's always going to be the same as that when grouping works. In other words,
Okay.
if you do not get a linear term that's the same, you've made a mistake or else grouping doesn't work for this. Now, notice what I can do. I can do something that you're probably not very used to doing, but I can factor out a binomial term here. From this expression, the greatest common factor is x minus 3. What's left?
Um,
When
do I more?
I say what's left, what factoring means is I'm dividing each term by this factor. So to figure out what's left, I just divide both terms by x minus 3. What do you get?
So it'd just be 4.
Hold it. Go left to right.
Oh. So would it just be x squared plus 4?
You got it. That's what factoring is dividing each term by that factor. Okay? If I take these two binomial terms and FOIL them back together again, I will have the cubic that I started with. Now, this is a linear factor. By the fundamental rule of algebra, if I'm trying to find the zeros, then I'm setting this whole thing equal to 0. So this whole thing is equal to 0.
Okay.
That gives me my answer, because the fundamental rule of algebra says that if you multiply any things together and you get 0, at least one of those things has to be 0.
Right.
So I can state that this is 0, which gives me a solution of x equal 3. See why?
Yeah.
And I can state that that's 0. Well, unfortunately, x squared plus 4 can never be equal to 0. It's a quadratic that has imaginary solutions only. The imaginary solutions are plus or minus 2i. So I guess we can say that. You see how I get x equal plus or minus 2i?
Yeah.
Okay. So if I really wanted to chop it all the way down to factors, I got x minus 3, x minus 2i, and x plus 2i. If I take those three things, multiply them together, I will get the original cubic. Now, the question said, what are the zeros? What's the answer to that?
Would it be... Okay, so one's got to be x equals 3, right?
Right?
And then another one has to be...
No, imaginary zero or imaginary solutions don't cross the x-axis.
Oh, okay.
Okay, in other words, let's look at this function, y equal x squared plus 4. That is a parabola shifted up by 4 units. So it looks like that.
Yeah.
Notice it does not cross the x-axis ever, because it has no real solutions. It has no real zeros. It has only imaginary zeros, and imaginary zeros don't show up by crossing the x-axis. So I'm not even sure that you'd want to give those as an answer. It kind of depends on what your teacher's been telling you about imaginary solutions. Typically, what happens in math, hold on a second, is when you are factoring a cubic or higher, you factor it down to its linear factors and irreducible quadratics. X squared plus 4 is an irreducible quadratic. So in reality, if somebody gave me a test and they said break that thing down, factor it, this would actually be my answer, x minus 3 times x squared plus 4. Because this x squared plus 4 is an irreducible quadratic, so I don't break it down to its imaginary solutions. Those don't really help me when I'm looking for zeros. It's just a lot of extra work, and so typically this is your final answer. Now, whether that's what your teacher is wanting or not, you'd have to ask her. But I've got books that say you break it down into its linear factors, that's a linear factor, and non-reducible quadratics, which means if this was x squared minus 4, well, it's no longer an irreducible quadratic. I can factor x squared minus 4 into x minus 2 times x plus 2. So if it's a quadratic that has real solutions, you must break it all the way down. In other words, this would be my solution if that had been an x squared minus 4. I would keep breaking that quadratic down as long as it had real solutions. And then my solutions would be x equal 3, x equal 2, and x equal minus 2. And those would be 3 places where the curve crosses the x-axis. In other words, all 3 of them would be zeros.
Okay.
Whereas the one that they gave us is only going to cross the x-axis in one spot, and that's x equal 3. Okay?
Okay.
How about another one? Let's see if all of the ones they've given you lend themselves to grouping.
Well, she really only gave us like one of those today.
Okay. So you, in other words, you have not had to try to figure out how to find the zeros of a cubic by any means other than grouping or your calculator.
Yeah.
In other words,
Well, I mean, the way that
go ahead.
she would give us other questions like, hold on, I'm trying to think of one. That would be like, let's see.
Well, there are other techniques to factor cubics.
Yeah, she would do this weird.
Right.
It was like
rational factor theorem
yeah.
and zero remainder theorem.
Yeah.
Let's talk about that. I didn't know whether you were at that step yet. That's what you need to use for most cubics. Okay?
Okay.
Let's take that last cubic. What was it? It was x cubed minus 3x squared plus 4x minus 12. Let's say I didn't know how to do this by grouping. There is a theorem that says if this polynomial has a rational zero, you know what that means, right?
Yeah.
In other words, not square root of 2, that's an irrational zero. In other words, if it has a zero that you can write as a fraction, then the numerator will be p, a factor of the constant, which in this case is 12, and the denominator will be a factor of the coefficient of the highest term. In other words, the coefficient of the x cubed term. Okay? Well, this would be particularly hard because factors of 12, let's list them. Plus or minus 12, plus or minus 1. And these always have plus or minuses in front of them. I also have plus or minus 6, plus or minus...
Square rooted at some point?
What's that?
Do you square root it at some point? Is that why it's like that?
No, just bear with me.
Okay.
I have two other factors of 12, plus or minus 3 and plus or minus 4. So those are all my possible numerators. That's what this theorem says, that if your zero is a rational zero, then its numerator will be a factor of whatever the constant is. So you have to allow for all factors, 12 and 1, 6 and 2, 3 and 4. It also says the denominator will be a factor of this coefficient. Well, in this case, that's plus or minus 1. Which means, since the 1 is on the bottom, that my possible solutions are those 12 numbers right there. Okay?
Okay.
And the way we figure out, if we have to solve this from scratch, and somebody said you can't use grouping, well, this is the way I would start. And then I would start testing one by one these numbers. And I would use synthetic division to do it. You know about synthetic division?
Yeah.
Okay, let's do, I always start with the smallest numbers and work my way up. So I would put the 0, I'm going to suggest the 0 is 1. And I would synthetically divide it into that polynomial until I produce a 0 remainder. Are you good with synthetic division?
Yeah.
Okay, well let me do it then. In other words,
Okay.
if you weren't good with it, I'd ask you to do it. But just to save time, I'll do it. Notice that we get minus 10 as our remainder.
Mm-hmm.
That tells me 1 is not a 0. So the next
Right.
thing I would do would try minus 1. That's not going to work either. We already know what the zeros are, right? The zeros were 3. There was only one of them. Well, since we know what it is, let's try 3 just so I can show you that this is a trial and error process, and you just kind of have to work through it. You're never going to have more than one of these on a test because they're like 20-minute problems. They truly are, because it's such a trial and error process. Well, if I bring down the one here, 3, 0, 0, 4, plus 12, bingo. If that remainder is a 0, then we found a 0. Not only did we find the 0, but we found the remaining factor. In other words, this 3, the fact that it produced that 0, we've satisfied the 0 remainder theorem. So I now know that one of my factors has to be x minus 3. And my other factor is this quadratic we got. That's a quadratic, which is x squared plus 0x plus 4. Remember, that's what we got when we did it by grouping. You can see why you would want to use grouping wherever you can. It's because this process is as tedious as it gets in mathematics in terms of finding the 0. In other words, assuming they give you no other information, this is the only way to do it. If you don't have a calculator. If you have a calculator, then you graph this function and you look and see if there's any zeros that jump out at you. And 3 would.
Okay.
It would cross the x-axis right at 3. But usually when they give you these problems, they're not calculator problems. You know, any chimpanzee could solve it with a calculator, but to do it by hand is the trick and the hard part.
So if
Go ahead.
the x-intercept is 3, then would the y-intercept be negative 12?
Well, the y-intercept is always wherever x is equal to 0, right?
Right.
Well, all of the terms that have x in them go away when you let x be 0. So the y-intercept is always that constant.
Huh. Okay.
Y-intercept is really easy to find compared to the x-intercepts. The x-intercepts, we have to set this whole thing equal to 0 and then try to figure out how to factor it. But
right.
the y-intercept is a piece of cake. Always remember the y-intercept is where x is 0, the x-intercept is where y is 0. So if we're
Okay,
going to solve x-intercept, we're going to set y equal to 0.
Okay. So she also asked us to like plug this into our calculator, which I did in class, and find the turning points.
And find the what?
The turning points of the graph, which I think it's 0, because it doesn't really change direction, it's just positive the whole time.
Let me pull up Wolfram Alpha real quick here and graph this thing and let's see what it looks like. Wow, I haven't been using Wolfram Alpha enough, I guess. It's not on my main menu. I need my keyboard for this. Hold on. So it's y equals x cubed minus 3x squared plus 4x minus 12. And the beauty of Wolfram Alpha is it shows you what you typed in. In other words, it gives you that feedback, which is a wonderful thing for a calculator to do. I hate the TI-84
Yeah.
because it doesn't tell you that. And if you have a complicated function, it can be really hard to get it in there right. You know, if it's got like 4 sets of nested parentheses and stuff, then it's hard to get in there. So having feedback is really a nice thing. It shows you the graph on 2 different scales. This is zoomed way out. That's zoomed in. You can tell the grid is different. But you can see where the 0 is.
Yeah.
At 3. And in fact, Wolfram Alpha gives you the zeros. It gives you the only real root is 3, and then it gives you the complex roots also, minus 2i and plus 2i. Now, also, you asked, where does it turn? It doesn't. Notice what this
Yeah, that's what I thought.
This is always increasing except at one spot, which is where x equals 0, and at that spot, the tangent to that curve would be a horizontal line. The x-axis is the tangent to that curve. So that's a weird question to ask for this particular function, because usually when she says where's the turning point, what she means is she has a graph. Hold on. Her graph looks like this, and there's a hook in it like that. Okay? A typical cubic function could easily look like this. It can have 2 local extreme points. Well, there's one, and there's another. And at both of those spots, the graph would turn. In other words, I'm increasing up to my first x, then it's flat, and then it starts decreasing. Down to my next x where it's flat, and then it starts increasing. So that's what they mean by where does it turn. So it's a bit odd to ask that question when the curve looks like this, because it doesn't turn anywhere. At no point does it turn and go in the other direction. In other words, it's almost always increasing. At specifically right there, if you were to draw a tangent line, it would be 0, slope. And that's what calculus is all about, is figuring out where a function turns, where it stops increasing and starts decreasing. Or better yet, if my function looks like this, knowing where it turns is huge, because if my function looks like this, well, I know that's a very special point on the x-axis. That gives me a maximum value for that function in a certain range. In other words, if I was looking between 0 and 10 on the x-axis, and I wanted to know where my function had a maximum value for y, well, this is a pretty critical point. That's its maximum. In other words, whatever this number is, let's say it's 5, but what this would mean would be that when x was equal to 5, my function would have its maximum value. And when x was equal to, we'll call this point 8, it has a minimum value in this range. And you always have to define your domain, because clearly up here is a higher value and down here is a lower value. But calculus is all about finding these what are called local extreme points, which are local maximums and local minimums. And
that's just what you can view, right?
Well, the definition of a local maximum is that there's a point to the left and to the right that are less.
Okay.
The definition of a local minimum is that there's a point to the left and to the right that are greater. And you can't produce that unless you have a curve. And it has to have a slope of the tangent line is going to be 0. In calculus, first derivative means the slope of the tangent line. So finding these local extrema is really easy with calculus because you take the first derivative of the function, you set it equal to 0, and you find this point and this point, because both of those points have a tangent line that is horizontal. And that's the only place on the curve where the tangent line is horizontal. Notice that the tangent line there has a positive slope. Tangent line here has a positive slope. Tangent line there has a negative slope. So finding the places on a function where the tangent line is horizontal or has a 0 slope is a huge thing for calculus and mathematics for that matter. It allows you to do all kinds of things that we couldn't do before. All right, I don't want to get too lost in my calculus here. What other, we got time for maybe another problem. Do you have one?
Well, she says to predict the end behavior of that as well.
Okay. I'm glad I didn't get rid of my graph. End behavior is what happens when x goes to infinity or negative infinity. In other words, there's right-hand end behavior and there's left-hand end behavior. If you look at this function, what happens to y as x goes to positive infinity?
Okay, so the y goes to infinity too.
Yeah, what happens to y as x goes to negative infinity?
It goes to negative infinity too.
So the end behavior, the left-hand end behavior is negative infinity. The right-hand end behavior is positive infinity.
Okay.
You could also figure that out algebraically. As you let x get bigger and bigger and bigger, this x cubed takes over everything. So as x goes to 1,000,000, in other words, when you're trying to figure out end behavior, the only term you have to pay any attention to is the highest degree term. I can basically cross these three out and substitute positive infinity for x to the third power, and it gives me positive infinity, right?
Right.
Now substitute negative infinity. Well, if you cube negative infinity, you get negative infinity.
Right.
So that is an algebraic way of determining your end behavior, is to take just your highest degree variable only and let x go to infinity and see what you get, or let x go to negative infinity and see what you get.
Okay.
And it's not always as easy as you might think. In other words, you can have this situation where my function might be y equal 1 over x. Now what's the end behavior?
The end behavior of y. So she has us like say it weird, like as x approaches infinity, f of x.
Okay, I have no problem with using f of x notation instead of y. They're the same thing.
Does that mean the same thing as y?
F of x is the same thing as y.
Oh, okay.
Okay, and what she's talking about is this, and she's talking about limits. In other words, what is the limit of f of x as x goes to infinity? Well, goes to 0. If I graph that function, here's what it looks like. Hyperbolic. There's two asymptotes. There's a vertical asymptote there. X can never be equal to 0. And there's a horizontal asymptote there where y can never be equal to 0. But if we look at the curves, we can see that as x is going to positive infinity, y is approaching 0. It's approaching that horizontal asymptote. And in fact, that's what horizontal asymptotes are, is what the function approaches as you go to infinity. So as x goes to negative infinity, what would y go to? or f of x?
So y would go to
Look at the
negative.
curve. Yeah. This is the f of x axis, and this is the x axis. So what happens as x goes to negative infinity?
Then y goes to negative.
No, y is approaching 0.
Oh.
So that limit is also 0. That's what end behavior is. It's what does the vertical, what does f of x go to as x goes to some number?
Okay.
We can see that as x approaches 0, y goes up to positive infinity. And as x approaches 0 from the left-hand side, y goes down to negative infinity. So this concept of limits is one that, it's a little soon for you to be taking limits. So I'm a little surprised. Usually you don't get into that until pre-calc. But anyway, hopefully I've been helpful tonight. And unfortunately, it's 6 o'clock, so I got to run.
Oh, it's okay.
I will talk to you next Wednesday. Now, should I just start calling Nick at 4:30 and you at 5:30 instead of the other way around?
Yes, Nicholas usually gets home before.
That seems like it's the way it's been for the last few months. So
okay.
I'll make that note, and next week I will be contacting Nick at 4:30 and you at 5:30.
Okay, sounds good.
All right, Anna. Have a good week. Talk to you next.
Thank you.
Bye-bye.